Hello, it is I, Dr. Brian Lorgon 111, and I have got something wild for you guys today. It is fractals in Minecraft, computed via a command block computer. And I am going to try to explain what's going on here. We've got a beautiful picture of the Mandelbrot set that has been drawn in colored wool by a command block computer, and I'm going to try to explain it. But honestly, while this is the product of a fun, lazy Saturday for Brian, who is a math geek with a PhD in computer science, at the same time, if you guys don't follow all of this, you get a pass. It's okay. While I start to talk about it, I'm going to click. Anytime you're computing lots of things with numbers, you definitely need a wolf pal along. I'm going to click the reset button, which will, among other things, teleport the wolf over to this corner so that we can start running this thing again, but it's also erased some of the blocks so that I can just kind of start running the computer, and so you can kind of see what goes on. There's a bunch of redstone that activates a bunch of command blocks, and as it does that, it then starts drawing the colored wool as it computes the color for each pixel, and the wolf here, Wolfie, is actually just used as a cursor to keep track of where we are, and keeps teleporting one space over so that we can put the wool above his head and keep track of which pixel we're currently working on. So while we are starting to recompute the top section of the graph, let's talk about what is the Mandelbrot set. Well, it is a graph on the complex plane. I'm going to hit escape here just so I can move my mouse cursor around. But basically, if we're looking at this graph, the x-axis, is the real axis. And this, up and down, the y-axis, is the imaginary axis. So this is the two-dimensional complex number plane. And the function that we are graphing is basically trying to determine which numbers can we repeatedly square and then add to themselves, and then square the result and add it to itself, or add it to the original number and square it and add it to the original number. If you do that process over and over and over again, one of two things will happen. Either it will diverge out to infinity, like if you take a number like 5 and you square it, you get 25, add it to the original number 5 and you get 30. If you square that, you get 900, add it to 5, and you get 905. And if you square that, like, it just gets bigger and bigger and bigger and goes out to infinity. And that happens for a lot of numbers. But if you do it with complex numbers, then because they have an imaginary component, when you square an imaginary number like I, the square root of -1, you get a negative, and so the negatives and the positives sometimes kind of balance themselves out. And so when you're very close to 0, but have small amounts of real and imaginary parts, it turns out that you can kind of keep running that thing, square it and add it to the original number, square it and add it to the original number, over and over and over again, and it never blows up to infinity. It always stays kind of bounded inside this little area. And so this graph on the screen, this funny black-shaped area, is the range of complex numbers that never end up diverging, as computed by this little thing here. And then all of the different colors on the edges for the numbers that are diverging out to infinity, depending upon how many steps it takes, how many iterations of squaring itself and adding it back to the original number it takes before the number starts to diverge, determines the color. And so some of the colors on the edges, the orange and the magenta and the light blue, are only taking like 2 and 3 and 4 iterations to start to diverge out to infinity, whereas the later colors, the colors of wool that we have up in this thing being generated, are things that are taking a longer amount of time before they diverge. And then the black is things that even after 16 iterations are still not diverging at all. And okay, so that's kind of an overview of what the Mandelbrot set is. So next up, how am I computing it? Well, briefly, I am mostly using the scoreboard. And so if I take a look at most of these command blocks, most of them are doing things to operations in the scoreboard. And so I can actually go and type scoreboard objectives, set display, sidebar, temp, for example. And we will see some of the temporary variables that I'm using being updated in the scoreboard through each iteration of the loop. And in addition to temp, I also have vars, which were kind of like the main variables that I was using inside this thing. And so you can kind of like see them getting updated during the computations. And then I also have some constants that are just kind of constants that I needed to use. And so these are a bunch of integers in the scoreboard that I'm using as part of the computation. But I think next up it may make sense to talk about some of the code. So now I think I'll probably put an overlay of a screenshot of some source code that I wrote on the screen. So I originally, in order to try to build this in Minecraft, the first thing I did is I just tried to build this kind of in real life in a real programming language. And the language that I like to use is F#. And so in, I don't know, like 35 lines of code here, you can see basically something that computes the Mandelbrot set, does the same computation that we're doing here, basically trying to compute 128 by 128 grid of colors of what we were going to draw to, wind up with this picture over here that is now kind of getting recomputed. When you see the little dots and speckles that are kind of in the middle of the picture, right around here, by the way, that's just where I poked holes in the wool because it's above the computer, and I wanted to have some sunlight actually shining down into the computer. So that's what's going on there, in case you were wondering. But basically, yeah, I originally, before I wanted to jump into the command blocks, I was like, okay, I need to know how to, compute this in my own head in order to make this work at first. And so first I wrote an F# program that computes it. And usually when you find code that's computing the Mandelbrot set, usually it would be something that involves floating point numbers. But the scoreboard that I'm using for all the computations in Minecraft, the scoreboard only handles integers. And so I had to rework the code a little bit just to work with integers. And so you lose a little bit of precision when you can't use decimal points and stuff after the decimal. And so basically I just ended up multiplying everything by around 10,000 or I think 5,000 in the code. And as a result, you get 3 or 4 digits in the integers that would be decimal points after the decimal. And yeah, basically I got a little program working in F# and I tried it out, and it computes this picture like instantly. Like you run the program and boom, it's on the screen. And I was like, okay, I have a little working program that I can use. And so now I just need to take that code and try to translate it into Minecraft command blocks. And I did that in a number of steps. This is kind of like the final result after I'd really kind of optimized and tuned everything. And so I guess rather than try to walk through all of it, I'll give you an overview and then point out a couple little particular features. So before we jump into the command blocks, there's something else I need to show you. So this is a different picture. This is still the Mandelbrot set, but in this case, I have zoomed in to one of the crinkly edges of it. And what's interesting about fractals in general, and the Mandelbrot set in particular, is when you go and take a look at their edges, they're kind of like coastline. It's kind of like infinitely long and crinkly and intricate. And so, yeah, it's a really fascinating aspect of a very simple function that you're using in order to compute the values. But basically, yeah, one of the interesting things about the Mandelbrot set is you can zoom into any particular aspect of its border, and it's incredibly interesting to take a look at what happens at some of the borders. And so here I've zoomed in on one of them, and the zoom function is important because that's the first thing I want to talk about in the command blocks. Okay, so we're back to the command block computer, and you can see that there's a stage here called zoom, and this is just for taking, I always compute from x and y of -64 to +64, because that is 128 by 128 grid that fits on this map. But I need to change those x and y coordinates, or sorry, x and z coordinates in Minecraft, because y is like going up and down. I need to convert those to the actual portion of the graph that I want to zoom in on for the Mandelbrot function. And so that's what this zoom function does. And if I do scoreboard objectives, set display, sidebar, const, I have 4 constants I use for zooming in to a particular portion of the graph. There's x offset and y offset and x scale and z scale. And so you just tune these numbers to a particular value to zoom in on a particular piece of the graph that you want to draw. But then those stay constant throughout the entire computation. And so that's what this zoom bit is doing. And so, I don't know, I'll highlight a few of the command blocks here. But basically it takes x and subtracts the f's offset and multiplies by k so that we can do floating point numbers inside integers, and then divides by the scale, and then it does the same thing for the imaginary part with the z coordinate. And once it's done that, then it calls Mandelbrot, and Mandelbrot function starts right here. And so this does the computation of the Mandelbrot, and so we have to start color, which is the number of iterations. We're going to start it at 0. We're going to initialize some other variables. And then we already saw some of the stuff that's going on here that, for example, is going to try to compute the modulus squared from the original code that I was looking at in F#, and then it's going to test and detect if it is starting to diverge, if it's getting too large and going out of range. And if it is, then it's going to call the draw function, which we'll take a look at it in a moment. But if it's not, it's going to do the next iteration in kind of the loop body. And so all of these command blocks are just updating a bunch of variables in order to compute the next loop body. And if we want to, then we go back to the next loop, which just reruns this portion of Mandelbrot right here and keeps looping and looping and looping until finally one of the conditions is met where either the colors have gone to 15 and we've already gone through 16 iterations of the loop, or if the thing is trying to diverge over here and it's getting to be too large of a number. And if that happens, then we go over to here and we actually draw the next pixel on the screen. You can see the pixels kind of getting drawn over there, little wool blocks appearing in the distance. Each time we have computed a color and we draw it. And so drawing it actually happens over here. And so here you can see I've got the colors of wool. And so basically I'm simply testing the color value to see if it is 1 or 2 or 3 or 4 or which number it is, and depending upon which one it is, it goes and lights up, and then it is going to execute at Wolfie. It's going to set a block way above his head to a wool color of 0 or 1 or 2 or 3 or 4, which are all the different 16 colors of wool. And so that draws a particular color of wool 20 blocks above Wolfie's head. We're too far away, so Wolfie isn't rendering, but he's out there, and we see wool blocks appearing over there. And so then after it draws, then it simply needs to add x to 1 in order to move 1 spot to the right. It's going to teleport Wolfie 1 spot to the right, and then restart the zoom function in order to just start the whole program over again. And then every so often, it needs to test and see if x has gotten all the way out to 63. And if it has, then basically we need to start the next row. And so there's some stuff that kind of resets some of the variables and starts the next row, teleports Wolfie 128 blocks to the left and 1 block down in the z in order to kind of start him on the next row. And we start the whole computation again. Yeah, if you followed any of that, at this point, it sounds kind of simple to get here. It did take me about 9 hours of programming and reprogramming and optimizing this to make this run. So you can see I've been talking about this for a few minutes here now, and we've only managed to compute, if I update the map, some more of it will draw in at the top. You can see a few more pixels kind of coming in. But it is a slow process. It definitely, where is it drawing right now? It's drawing somewhere over here, I think. No, here's the wolf, here's the cursor, here's the pieces of wool that are getting computed right at this moment. And so, yeah, you can see it's going, I don't know, maybe 1 block a second. When it gets into things that are darker colors, it takes maybe 1 blocks every 2 seconds or something. And so it goes not too slowly, but definitely not quickly. It took about 10 hours to draw the entire thing here. And yeah, that is a result of me doing a lot of optimization on this command block program, because while this isn't using much CPU, like if I go into like Task Manager on my computer, I'm only using like 5% of my CPU. The thing that slows it down is every time we have a comparator, one of these guys right here in Minecraft, that is doing a test, comparators take 1 redstone tick to run. And a redstone tick is 1/10 of a second. And unfortunately, there are a few tests that we need to do in each iteration of this loop. And so each time you need to do a test to see, for example, if we've gone through 15 iterations of all the colors and We've already gotten from wool 0 to wool 15 to black, and we're deciding that the thing is not escaping. That's going to take 1 redstone tick, 1/10 of the second to run. And the inner loop, in order to draw this whole picture, needs to run over 100,000 times. And so basically each redstone tick that you add to the inner loop, to the hot path, causes the whole thing to take like 2 hours longer of wall clock time in order to complete. And so originally I was doing things like if I had to knot something, if I was doing some redstone logic and I wanted to use knot, I would set down a redstone torch. Well, each redstone torch is another tick, another 1/10 of a second, another 2 hours that it's going to take to compute this thing. And sometimes I had different components of it in different places. And so I'd run something in a little fill strip over here, and then I'd go and I'd start running something else in a fill strip somewhere else, and that was another 1/10 of a second. And so I kind of redid a bunch of the command blocks, the layouts, so that I could run them all at once. Because if you use a fill command and fill an entire row with redstone blocks, then you can run a whole series of commands inside a single redstone tick. And that's the only way that you can kind of do anything in a reasonable amount of time, where a reasonable amount of time is less than 1/10 of a second for a computation. And so I kind of had to do a bunch of refactoring and even some like speculative execution here where I'm doing a test, but at the same time I'm testing if we need to exit out of the loop. I go ahead and I continue executing a bunch of other things over here. And if over here I discover inside a single tick that something is going wrong, I end up going and, for example, erasing this block and replacing it with a stone block and then replacing it with its original command back a moment later, so that I can do multiple computations inside the same tick that still involve a compare operation. It's kind of ridiculous stuff. I didn't do any, there's other kinds of computer science optimizations I could have done with loop unrolling and using more temporary variables. I was already using, I don't know how many temporary variables. I've just got like 3 temporary variables here, but then I've got these other, I don't know, 10 variables here. It was already getting too much for me to keep track of in my head. And so there are other types of optimizations I could have done to try to make it run faster. And then the other thing I was considering doing, there's another wolf over here called P0 that I was going to be trying to make be a little wolf processor for doing some parallel processing. I was thinking then of taking this whole computer here and stacking like 8 of them vertically in the y-axis. And then rather than keeping score in the main scoreboard, now in the latest snapshot, entities can have score values. And so if each one of these computers had its own wolf named like P0, P1, P2, P3, and rather than putting the integer computation, the temporary variables in the main scoreboard, I could attach them to each of the individual wolves. Then I could have like 8 computers that were all doing separate computations and running in parallel at the same time. And one of them would be drawing kind of like the very top of the map, and the next one could be drawing, you know, the next section of the map. And so let me get out into some sunlight here. And so one of them could draw up here, and the next one could draw up here, and the next one could draw in the middle over here, and so on and so forth. But even if I did like 8-way parallelism like that, assuming I could get it to work, it's still just going to cut things down from like, 10 hours to an hour and a half or something like that. And so I never ended up bothering to do that, but there's lots of fun things you can do. In computers to try to speed things up. But I was happy enough that I was able to render a picture like this overnight, just by leaving this running and going to sleep and waking up the next morning and seeing what it did. Yeah, so that's what I did. What else is there to say? I don't really know what else to say about this. I know people will want a map download, and so I will provide a map download in the description of this video. So if you want to take a look at it and poke at it, you can do that. I'm not sure how interesting it will be. There are a few signs that kind of suggest what's going on, and I showed some source code in the video that you might be able to use to kind of backtrack and figure out what I was doing. But at the same time, I did this all on like Saturday because there was a whole lot to keep in my head at once in order to get this going, and I was afraid that if I went to sleep and tried to work on it again the next morning, I would not be able to pick up where I left off. It was fun for me to do. It definitely makes pretty pictures at the end of the day. I don't know that it has any utility apart from this. I don't know that I'll do any more of trying to draw fractals in Minecraft, but it was a fun little project, and I just posted a couple of screenshots on Reddit over the weekend, and people seemed to really love it, so I decided, all right, I need to make a video and try to talk about it, but I don't know how much people will be able to digest here. So, yeah, I make command block computer that draws pretty pictures on the screen, is the one sentence summary. So I hope you enjoyed it. I hope that you guys are having a great day, and I'll see you again soon. Bye-bye.